like this. So in this case, I'm assuming lambda of x is alpha x squared. And more of the charge is here, and then over here. Right, so since more of the charge is farther away from the point, you see here and here, rather than in the middle, the electric field should be less, right? And plus, they're more angled. So if you take a piece from here and another piece from there, so this is the most charged portion of the rod, but the electric field cancels more on the two electric fields here. Whereas here, less cancellation happens, but the charge of the rod is not that strong in the middle of the rod. So it should be less, pretty much, from that argument. So then the electric field will proceed kind of similar to how we have it here, 2K d dq, and dq is going to be lambda dx. So I'm going to kind of, that portion, I'm going to kind of follow 2k d, and then lambda will stay in the integral alpha x squared dx over, and then the x squared plus, and then if I'm 3 meters away, then 3 squared to the 1/2 power, right? From 0 to 0.5, then the alpha will come out. So the difference is that for the non-uniform, you're putting the lambda function, what lambda function it is, and only the alpha, this constant, is coming out, not the whole lambda itself. And then now you have E total Y is going to be 2 times 9 times 10 to the 9th. And then D is going to be 3 meters. And then alpha comes out. And then whatever that integral gives me. X squared plus 9 to the 1.5 power. And then here, alpha, I can use the alpha that I got when I was doing the side of the rod, right? So I don't have to find out again what the alpha needs to be. In other words, to find the fudge factor, once I found it once for that rod, for the charge of that rod, I don't need to find the fudge factor again if I'm trying to find the E field there, you see? So I can, where was that other one that we did? I think it's here somewhere. What did the alpha come out? Let's see. Oh, here it is. Alpha came out 12Q, right? 12Q in the case where the lambda of x was alpha x squared. We did the integral here, and alpha came out 12Q. If I'm going to do the linear, then it's 4Q, you see? So it'd be more 12Q in this case. So then I take that and put it here, 12Q. So 2 times 9 times 10 to the 9th times 3 times 12. And then the Q in my case is 10 nanocoulombs. And then whatever the integral gives me. And then the 10 to the 9th, 10 to the minus 9 cancel. Okay, let's see what that integral gives me. Okay, so now we have x squared over, this one changes completely. So you have x squared plus 9 to the power 1.5 power. X squared plus 9 to the 1.5. Is that right? Yep. Oh, and then I go from 0 to 0.5. Because this one I'm doubling it, right? Because of the symmetry. Then go. Okay, so let's put that in my calculator. So the integral came out 0.0015. Point 0.0015 556 0.00150 556. Okay, 296. Okay, so this the integral came out that. Then I multiply it by 10. Oops. 0.01556.29639 times 10 times 12 times 6. 6 times 9. .76. Ooh, it's not that much smaller than the uniform, even when it's x squared. Let's see here. Where was the uniform? Yeah, I got 9.86 for the uniform. So going to a non-uniform alpha x squared, it drops, but barely noticeably. So the answer is 9.76. You see? So it drops by 0.1. Let's see here. 9.77, yeah, right there. Perfect. Now, what if I go closer? What was the answer when I was like 10 centimeters? When I was 10 centimeters away, what was the answer? Like 1700, 1800, right? I think the drop in the electric field is going to be more noticeable when I'm close. Remember, the electric field 10 centimeters away was 50 centimeters away was 200. Yeah. See this data that I had? I'm kind of comparing it to this data when it was uniform. 10 centimeters was 1270, 20 centimeters was 640, 30 centimeters was 400. So you see, they were in the 1,000, 600, 400. But now when I go close, what happens? See, 10 centimeters, it's only 200. Then, well, actually, let's see here. Yeah, 200. Then it goes 260. Then it drops 250. Yeah, it's much weaker. So in other words, the fact that there's more charge here and more charge here, the electrical field here is a lot weaker than it was when it was uniform. and then it starts dropping. But by the time you go very far away, the answer is not too much different than when it's uniform. It's slightly smaller, but not that much smaller. But over here, it's a lot smaller. So why is that here? Okay, so why is that? Well, when you are close to it here, you see the strong charge which is here creates an electrical field, very large electrical field like that. You see? And then these guys don't create very strong E field because there isn't much charge there. Okay, but the problem with these strong electric fields is they cancel. You see, the X component of this cancels with the X component of that, right? So most of it cancels. So there's only the Y component survives, you see? So when you get closer to it, the fact that the strong charges at the ends really kills it, kills the electrical field, you see? So yeah, it does make sense. Okay, let's draw the field lines just so we can see what it looks like. Yeah, it goes like this. Kind of similar to the other ones, but it's weaker here. Definitely a lot weaker. Okay, now let's do take these rods, bend them into a circle,